So we're gearing up now, changing a little bit the subject to talk about disks. So the next talk is by Ruth from University of California, Santa Barbara.
Thanks. All right, so if we want to know how planets form, we need to know what they're forming out of, and what they're forming out of is disks. That includes both how much material is available to form planets, and what that material is made out of, what its temperature is, and how all of the answers to those questions evolve over time. So the way that I'm going to organize this talk is, after a brief introduction, I'm going to organize this roughly around disk age, around that evolution over time. But I'm also going to start in the first half by doing a number of calculations to show you how you estimate disk properties. And then in the second half, we'll come back to looking at some observations and how they relate to those estimates. Okay, so as we all know, planets and their disks form out of form as a result of star formation. This is the Orion star-forming region. Here, these little insets are forming stars, and around them there are protoplanetary disks, or you could call them protostellar disks. It doesn't really matter. People use the same word to mean both, especially at early times, because fundamentally they are just the dregs of star formation. And actually, while this plot is up, I want to make 2 points that I'm not really going to emphasize that much during this talk, but that should actually be forefront in your mind, thinking about how to move forward in this field, I think, at least. The first one is that planetary systems form in different environments. These proplyds, they're called, are very dramatic because they're sitting in the middle of Orion. There are some very bright stars in the region. They're being photoevaporated by their neighbors. So your stellar environment can actually affect the type of planetary system you form because it affects your disk. So there may be some creative ways going forward to try to look for the effects of different environment in which planets form. And the second one is related to what I just said, which is that properties evolve over time. And these are young stars. They haven't actually settled into their main sequence properties yet. That's true even for G stars during the lifetime of a protoplanetary disk, but it's even more true for M stars. So if you're thinking about stellar properties when you're thinking about disks, you really need to go to pre-main sequence evolution tracks to understand their luminosities, and so on, if you're doing detailed modeling. Okay. So,
we will take a look at Orion, but it's the day after.
Too bad. Perfect, though, for those of you who are here. Okay, so here's a simpler star formation region. This is a dark cloud, and it's a little hard to see in here, but this is actually pretty cool. If you look around the edges, you can see, reddened stars because of dust extinction in this cloud. And the authors of this paper actually were able to make a map of the density of this cloud using the amount of extinction compared to distance from the center, and show that this is marginally unstable to collapse under its own self-gravity. So this is going to be a star formation region as well, a much less dramatic one. So what happens when a cloud collapses to form stars? Of course, it infalls under its own self-gravity. There's some rotation, as we heard about yesterday. And the result is, much as you throw out pizza dough, rotation gives you a flat disk. You end up with a disk that's processing material onto the young star. So infalling material gets processed through this disk onto the star. And this disk is where planets are forming. So at large distances, it's made of gas, dust, and ice. In the inner regions, it's too hot for ice, and you just have gas and dust. All right, so this is a protoplanetary disk. This is the site of planet formation. But of course, once you've formed planets, even in old systems like ours, you still have a disk. And we can see it in the solar system in what's known as the zodiacal light. If you look at the right time of year, so that the ecliptic plane is coming up sharply above the horizon just at dawn and dusk, you can, in a very dark place, and this is from Parnell, you can see scattering off of dust that's in the plane of our solar system. And this is what's known as a debris disk. We have a very faint debris disk compared to the debris disks that are currently observable, but probably most stars and most systems have debris disks. All right, so that's my brief overview. And now what I'm going to do is go to the board and do some calculations. Then I'll come back to observations on the computer afterward. All right. So let's just start with a little bit of terminology. I said that a protostellar disk is a disk that's processing material on a forming star at early times will be embedded in infalling gas. Gas and dust, sorry. Most importantly, dust, because that's what generates the opacity. And these are known as class 0 and class 1 sources. And typically, this is thought of as being, the epoch of star formation. But really, we have to think about whether any of that material will end up becoming part of the planetary system. And it probably won't, but it's worth actually taking that question seriously, and I'll come back to that in a second. Then you have a protoplanetary disk. And again, sometimes these two terms, protostellar and protoplanetary, are used by people interchangeably. Or a T-Tauri disk, or a class 2 source, are unembedded. So observations are easier. You still have lots of gas. We assume, usually, that the dust to gas ratio is something like 10 to the minus 2. This is the ratio between solid material and hydrogen and helium gas by mass. This is based on the abundance measurements that Dave showed us yesterday. And so we still haven't lost the gas in the disk, but it's unobscured by infalling materials. The idea is that the infall from the cloud has mostly stopped. And then you can have, you can have a classical T-Tauri disk. Still shows evidence of accretion. We'll talk about that more in a bit. A weak-lined, yep, oh, no. T-Tauri disk, or a passive disk. As thank you. No observable accretion. Okay. And so this disk is just sitting around. And then finally, so again, these are still protoplanetary disks. They have a lot of gas. Then finally, when the gas is mostly gone, then we start calling it a debris disk. And debris disks can still have a little bit of gas. Actually, there has been gas observed in debris disks, but it's a very small amount and is sometimes thought to come from actually comets that are being disrupted as they fall in toward the star and emitting some of their gas. Okay. So this is just a terminology. So starting from the youngest disks to the oldest. Are there any questions about this? They're all using the same words. Okay, great. Oh yeah, oh sorry, yeah.
Do you call them T-Tauri disks just because they're usually long T-Tauri stars?
Yes, well, T Taurus was the first one discovered, so they're named after that first object. That's right. So a T Tauri star, I mean, maybe you call them T Tauri stars more than you call them disks, T Tauri disks, but that's what I mean. Okay. Yep.
Just about the classical T-Tauri disks. So what's the average accretion rate?
So I'll show you a plot in a little later and ask me again if you didn't get your answer. Is there an eraser somewhere? Here. All right. Okay. So now that we have some terminology housekeeping out of the way, let's also write down for reference the standard reference point we have for the masses of these disks, and that is the minimum mass solar nebula. The minimum mass solar nebula was calculated in the 1977 and 1981 by Weidenschilling and Hayashi. So that was well before exoplanets. It was based only on the solar system. So the thought exercise that they did was to take all of the planets in the solar system, assume that they all formed where they are now, which we now know is a bit questionable. Assume that they were all the planets that were ever there, which also may or may not be true. Then add all of the hydrogen and helium you would need to get the solids that we see in our planets using the composition of the sun, spread it out, and ask how much mass you need. And Hayashi's version was like this. This is surface density in the disk of gas equal to 1,700 grams per centimeter squared. This was Hayashi's coefficient times distance in the disk divided by 1 AU to the minus 3/2 power. So there's nothing that says that this has to be right, but this is a very common reference point that people use to scale to. So it's worth keeping in mind. Okay, so that's the minimum mass solar nebula. And all right, so let's go from there and start talking about what happens in one of these young disks. So when the disk is obscured, we unfortunately don't have a lot of observational evidence to directly measure the masses of disks, or their rotational properties for that matter. And the reason is that they're sitting in obscured clouds that are infalling. Infalling material has velocities associated with it. It's very difficult to disentangle what is actually part of the disk and what's part of that material that's infalling onto the disk, but that isn't yet orbiting in a roughly Keplerian orbit. But nevertheless, most people think, largely based on numerical simulations and on the fact that accretion rates are very high at early times. You need to make, say, a solar mass star in less than 1 million years, or in some cases less than 10 to the 5 years. So you know your accretion rate has to be very high just to do that. That these disks are very high mass. You're essentially driving so much material onto the disk that their mass gets very high, and they end up being self-gravitating. That self-gravity can raise spiral arms in the disk that torques material onto the central star very quickly. So what's the, how do we write whether a disk is self-gravitating? So a disk that is, sorry. So a parameterization of self-gravity is the 2 raised q parameter. To really get the 2 raised q, you would do a stability analysis of a disk. I'm going to give you the quick and dirty way of estimating what it is, just to give you a sense. So let's imagine that we have a star. Here's our disk. You have a little patch in your disk with some length scale L. It's the radius of our patch, or the diameter of our patch. Yeah. Okay, so let's make it the radius, just for fun. Doesn't matter. Okay, and we want to say, can this patch collapse under self-gravity? It has some surface density, sigma, like we had before. So let's see. We can say pressure in the disk prevents collapse if the pressure force is stronger than self-gravity. So let me just go over here and quickly remind you, if you have a little patch of gas, let's say this is the z direction in your disk, in your patch of gas, you have some density, rho. What's the pressure force on this cube of gas? You have a surface area on top. So the pressure force on your fluid element is going to be equal to, let's see, P1, you have P2 on the bottom, P1 times the area on the top, minus P2 times the area on the bottom. So you have force per area. The difference between the top and the bottom gives you your force on your cube. So that's equal to your area times delta P. So the force per volume, and let's call this delta Z here, is going to be equal to A delta P over your volume, which is A times delta Z, which is equal to, in the limit, dP dZ. Okay. So if we go back to our little patch of disk, we want to know what is the pressure force in this patch of disk. We have, let's do it per mass. So force per mass is like P over the length scale of our patch of disk divided by the density. So that takes us from force per volume to force per mass. And we want that to be greater than gm over L squared, but m is our surface density times L squared. Let's call it pi L squared. This calculation does not merit putting in a pi, but I'm going to do it anyway because it ends up working out nicely. Okay. All right. So what does that mean? So remember that our ideal gas law says that P is equal to rho kT over mu. kT over mu is the isothermal sound speed squared. So I'm just going to use that here. So we have sound speed squared over L is greater than pi g sigma. These L's cancel out. All right. So what that means is that for L less than CS squared over pi g sigma, for small scales, pressure will stabilize this disk. All right. All right, what about at large scales? Well, in a disk, you have another force that will come in to help you. And again, I'm not doing this really informally quite the right way, but it at least gives you the idea. So what is the tidal force on our patch? In other words, if you have your star here, the close side is being pulled by the star more than the far side, right? So you have, if you're at a distance r, you have gm over m star over r squared is your acceleration on this side. Here you have gm star over r plus l squared is about equal to and we Taylor expand 1 minus 2L over R. So the difference here is approximately GM over R cubed times L. That's the form of a tidal force. And if you remember from Kepler's law yesterday, this is equal to n squared, as Scott wrote. And I'm going to write that as omega squared, just because when people are talking about disks, we usually use omega. But it's the exact same thing as n. This is the angular velocity of an orbit. OK. So all right. So now we have tidal gravity prevents collapse for omega squared L greater than that same g pi sigma. So for L greater than pi g sigma over omega squared, so at large scales. OK, so we have, so if we want, so collapse requires there to exist an L, a scale, such that L is less than those large scales, but it's also greater than these small scales where it's stabilized. OK? And that means that this number has to be less than this number. That means that the sound speed squared over pi g sigma has to be less than pi g sigma over omega squared. And that's the same as saying that cs omega over pi g sigma is less than 1. And this thing here is the Toomre Q parameter. So if Q is less than 1, your disk is unstable. And if it's greater than 1, it's not. So for reference, if you put in the sound speed here is referring to the temperature of the disk. If you put in the parameters here for the minimum mass solar nebula, you get a Q of about 30, depending on exactly how you plug it in. So the minimum mass solar nebula is very stable, and you could actually add a fair amount of mass to the nebula without worrying about instability kicking in. I guess one last point about this, I'll just say, is this, the instability scale, when these are equal, you get maximum, you get instability. And if you just quickly do it, set these all equal to each other, you'll get L is equal to CS over omega, which I'll show you in a minute is equal to the scale height of your disk. So that sort of makes sense. The scale on which a disk will first collapse is roughly its thickness. All right. OK, so at early times in a disk, it's being driven by infall from the protostellar cloud to high masses. And at those early times, it may be the case that disk properties are determined by the disk being marginally gravitationally unstable. And in fact, many people assume that, but we don't, again, have direct observational evidence that that's true. Yeah?
All equal to get maximum instability?
Oh, well, just the first place that it'll go unstable. Right? If you keep increasing your mass, when these start pulling apart from each other, the first scale on which they'll start pulling apart is where these are equal. And then once it's pulled apart more, then this one is more unstable than the ones nearby. I mean, you can do a real stability analysis and show that for real, but that's qualitatively what's going on. Does that make sense? Okay. Sure. Okay. All right. So that's early times. But once infall stops and the disk is no longer being driven by material from the cloud that can send it to such high masses, then it has to accrete under its own power. And that's not actually easy for it to do. And I will do another calculation to show you why. And this is sort of a long calculation, and the reason that I'm doing it is not necessarily because this specific calculation is the most important one, but because many of the sub-calculations that you do to estimate disk properties come in. And I also think it's interesting. Okay. So let's ask the question, how does the disk accrete once it's no longer being driven by such massive infall that it becomes unstable, has big spiral arms that can cause big torques? And the basic idea is that a disk is a Keplerian rotator, right? So the velocities that you're going, if you're in the inner part of the disk, are larger than the velocities in the outer part. And if you have material that's trying to move past each other quickly, you end up with friction or viscosity that causes it to try to come to the same velocity. And if you do that in a disk, you try to make these velocities equalize, what happens is that you'll remove angular momentum from the inner material and it will accrete toward the star. But if you try to do this just with the standard types of viscosity that work on Earth, it doesn't work at all. So that's what I want to show you. Okay, so let's imagine that we have another one of our little fluid elements sitting in here. Let's call this direction x and this direction y. So we're going to have a delta x here, and this is going to be much less than r, the distance from the star. So let's just take this piece here and forget that it's orbiting around the star, and just think about viscosity across our fluid element. The force, so this is v in the y direction. Again, this is the x direction. We want to know what's the force on our cube. What is the change in the y velocity with due to interactions in the x direction? So what's causing the interactions is the fact that our little molecules here are moving around with thermal motion. And the random motions of particles, just due to their temperature, right, is 1/2 mv thermal is like 3/2 kT, or I guess what coefficient you have here depends on what kind of average you want to take. So in other words, v thermal is like kT over m, which is the same thing as the sound speed squared. So I'm going to use the sound speed in here, but really the physics is the random thermal motions of gas particles. All right, so what happens near the edge of the box? These things are moving, and they move about a mean free path across the edge of the box, and then they collide with somebody else. And the somebody else that they're colliding with is moving at a different velocity, so they try to equalize their velocities. And the change in velocity that you get due to that collision depends on the difference in the bulk velocity here and the bulk velocity over here due to a mean free path. Okay, So let's see, what is the force on one side of the box? So to get that, let's just remember that, right, if you have some cross-section and it's moving at some velocity through a gas with the number density n, it's going at some velocity, then if we take this length is equal to the velocity times the time that's passed, then n sigma times the length is equal to the number of collisions. As you just multiply the volume times the number, and you get the number of things you've hit. Number density, you get the number of things you've hit. OK, so n sigma v is equal to the collision rate. OK, so the force on one side of our box here is going to be equal to the rate of particles crossing the side times the delta V per collision. Or, okay. So we have times times the mass of the thing that's doing the colliding. Okay, so what's the delta V per collision? Well, it's just coming from this gradient in velocities, right? So the delta V is like dvy dx times how far it's gone, the mean free path. The mean free path, if you put in the mean free path for this length here times n sigma, you get one collision. So the mean free path is equal to 1 over the number density times the collisional cross-section. OK, so that's what we need. So we have the force on the one side of the box is going to be, and this rate here is just like that over there. The rate of particles crossing the side is the area times the thermal velocity times the number density. Okay, so now we have our force on one side of the box here is going to be something like mu n a v thermal times dvy dx times the mean free path. Okay. So, but what we really care about is our total force on our box. So we need to, I guess I don't want to erase that, but let's see if I can get all right. Okay. So our total force is going to be this force on the right-hand side minus this force on the left-hand side. So we have mu, we're almost done, Na, V thermal, those are all the same, the mean free path. But now this is going to change, d squared Vy dx times delta x. So this is the difference across two sides. And if we want force per mass, what is the mass in our cube is just the density of particles in our cube times the volume of our cube. And we can just divide by that. And we'll end up with, by definition, dvy dt is like V thermal lambda mean free path times d squared Vy dx. Okay, so this is our diffusion equation. This is our diffusion coefficient, but here we call it nu, which is the kinematic viscosity. And what this is telling us is that the time scale on which, I guess I'm just going to make this a big bold T to try to differentiate it. So the time scale of the velocity change on the macroscopic scale is going to be something like this kinematic viscosity times the macroscopic length scale times the velocity divided by the macroscopic length scale squared. And this is, of course, then these can cancel out. And this is the standard property of diffusive processes. Okay. So let's just finish this thought then. So we did this for velocity, but if we're thinking about a little tiny patch at a distance that is much larger than our patch, then the angular momentum of that patch is just distance times velocity. And instead of having velocity here, we could just have angular momentum. So the angular momentum change, the time scale for angular momentum change over the size of the disk, right? So we're going to have L over the time scale for accretion. Now this is our accretion time scale. Is like our viscosity times angular, so this is now angular momentum. R Vy times L over R squared. And this is the distance from the star. And this is the length scale that we want to change our angular momentum over to have substantial accretion. Okay, so those L's cancel out, and we have our time scale is something like nu over R squared, which again was the thermal times the mean free path over R squared. Okay, so let's go back to our minimum mass solar nebula and put some numbers on that. Thank you. I'm going to actually invert it because I want to have the time scale. Okay. So let's put on some numbers. And so at 1 AU, in the minimum mass solar nebula. So first we need to calculate our thermal velocity. We need to know our temperature. And I'll mention in a moment how you calculate temperatures, but for now I'm just going to say at 1 AU, the temperature is roughly room temperature. So the thermal velocity, it's like sound speed is like a kilometer per second. You can do that calculation, but that's a number I like to keep in my head. Okay, and the mean free path is like 1 over n sigma. So now here are two important points about protoplanetary disks. Disks are cold and neutral. So the collision cross-section is just something like the size of an atom squared. It's like 10 to the minus 15 centimeters squared, 3 angstroms squared. And now we have one more thing to do to calculate that number density. We know from our minimum mass solar nebula what our surface density is. We can divide by the mean molecular weight, but we need to divide by the scale height of our disk. So let's just quickly show that what I said before is the case. And I'll reveal that after we've calculated the scale height. All right, so now we have our star. Once you're in the minimum mass solar nebula, you're not self-gravitating very much. So really all that matters for a gravitational force on a little piece of gas here at one scale height above the surface is the gravity of the star, the component in the vertical direction. So this vertical component here is gm star over r squared times sine theta, which is like gm star over r squared times h over r at a height of h. And then what's balancing that, right, is pressure. And this is force per mass. So pressure force per mass, we already showed, is like P over H, that's dP dz, times 1 over density. That should go from mass, force per volume to force per mass. Right? So let's these balance. So H, this is again Kepler's law, gm over r cubed is omega squared. P over rho is equal to Cs squared from the ideal gas law over H. So we have H is approximately the sound speed over omega, just like we said. Okay. So we can go back. And use that here. And so now we have H is like 1 kilometer per second over 2 pi over 1 year. That's our angular velocity around the sun. We do things in CGS. So this is 10 to the 5 centimeters per second. And a year is pi times 10 to the 7 seconds. So this is divided by 2 times 10 to the minus 7. So this is like 5 times 10 to the 11 centimeters, which coincidentally is something like the radius of the sun. Right. So just for scale, that means that H over R is like 5 times 10 to the 11 centimeters over 1 AU, 1.5 times 10 to the 13 centimeters, is something like 0.03. Right. So this is the aspect ratio of our disk, which is pretty thin, which is consistent with what your intuition is probably. Okay. And why is it really thin? Fundamentally, it's really thin because the gas is cold, so its sound speed is small compared to the escape velocity from the star. All right. So we have, so what is mu here? So this was, what is mu? Mu is, it's about 2.3 times the mass of hydrogen. Why 2.3? It's because it's H2, that would be 2 times the mass of hydrogen, and the 0.3 comes from the helium that's mixed in. And so, the surface density, we said, was 1,700 grams per centimeter squared. So let's plug that all together. And we get something like 2 times 10 to the 3. That's the 1700. Oops, I'm doing this backwards. We get something like 2.3 times the mass of hydrogen times 5 times 10 to the 11. Now I'm making bad use of the board, and I can't find my eraser. That's why. OK, there we are. And we divide by 2 times 10 to the 3. That's surface density times 10 to the minus 15. And if you plug this all together, then sort of magically, but not really, it turns out to be 1 centimeter. OK, so the mean free path in the protoplanetary nebula at the distance of the sun is about 1 centimeter. OK, so let's go back to this calculation here. So now we can calculate this. We have 1 AU squared over 1 centimeter times 1 kilometer per second. We get 1.5 times 10 to the 13 centimeters squared over 1 centimeter times 10 to the 5 centimeters. And that per second is going to come out. We have a 2 times 10 to the 26 on the top times 10 to the 21. Remember, pi times 10 to the 7 seconds is a year, so it's like 10 to the 14 years, which is greater than the age of the universe. So, no, this won't work at all. Bad, bad, bad. So this is fundamentally why it's very difficult to understand how protoplanetary disks accrete and how they evolve, and why we don't have good models for the evolution of protoplanetary disks that allow us to actually just use them to for our initial conditions. Okay, so there are 2 solutions to this that both remain viable. Okay, the first one is that you have some source of turbulence that gives an effective viscosity. So nu, now instead of being the sound speed times the mean free path, is some microscopic velocity that's based on that turbulence times some microscopic length. We don't know what these are, but we know that the velocity has to be less than or equal to the sound speed, because otherwise you get shocks and energy dissipation, and it won't last very long. And we know that the length has to be less than or equal to the scale height of the disk, because you can't have things going vertically larger than the size of the disk. So we say that nu is equal to alpha times cs times h, where this is a parameter of ignorance. And it is less than 1, and that's all we know about it, and it does not have to be constant. But results are very frequently quoted in terms of alpha, because then at least you're scaling to something, you know what you're scaling to. So it's useful in that sense, but it really, we don't know what it is. It doesn't. So the best possibility for generating this, it works very well in other astrophysical situations. It's not the only possibility, but it's the only one that's actually been shown to work at all so far in this context, is the magnetorotational instability. Or MRI. But this requires ionization. And it actually doesn't require much ionization. It needs an ionization fraction of something like 10 to the minus 10. But Actually, protoplanetary disks are so cold and so dense that it's very difficult to get an ionization fraction of 10 to the minus 10, plus or minus a couple of orders of magnitude. And so it's not clear that the magnetorotational instability will actually work. And so in that picture, the standard picture of disk structure that you might draw from that looks something like this. It's just a possibility. You know, 0.1 AU. Here it's ionized because hot, very close to the star. So you have the MRI works there. Then here you have a dead zone where you could have surface layer accretion, maybe up at the top, because high energy photons can come and ionize the surface. And then out here, maybe this is a big tilde out beyond 10 AU, you might be X-ray ionized from X-rays from the star, just because you have a low enough column here that they can reach the center enough for the MRI. Okay, so that's solution number one. That's the older solution that, and it remains viable. Then we have solution number two, which is has been getting attention recently. I'm just going to do this very briefly. And that is to say that you have a strong B field, magnetic field, that you accreted from the cloud. So, you know, pulled it along with you during disk formation. And you end up with a structure that looks like this. Here's your star. In the inside, you still are hot, still hot. But now, in this intermediate region, what you end up with is a calm midplane, but angular momentum transport is happening because of a wind. That's being driven off of the surface. And to get the details of this, this is highly dependent on non-ideal MHD. So what that means is you can't assume that the gas is all ionized. You have to really pay attention to the photochemistry in the disk at very low ionization fractions and understand exactly how ionized it remains, which depends on your grain properties. It's a really nasty problem. And it's, you know, people are working on this, but it's hard to do. And you actually have the same problems doing these sorts of simulations. So effort is being put into this. We still don't know what the answer is. It's difficult and depends on very hard to simulate non-ideal magnetohydrodynamic simulations, and they need to be global. So I'm looking forward to the results that people who are doing this will have in the relatively near future. All right. Yeah. Sorry, this is actually a wind. Material is being, coming off, but they follow magnetic field lines, so it's both. All right. Okay, so I want to pretty soon get to looking at observations. So I'm just going to say, oh yeah, thank you. Yeah.
Accretion is such a central component of our understanding, including X-ray binary. I think the alpha model was suggested like 30 years ago. And we still don't understand.
Yeah, I think in those highly ionized, high energy cases, the MRI actually works pretty well. So it's understood better there than here. But I agree with you. It's fundamental to understanding the structure of the disk that we're working with. And I think this is really the main reason why we don't have a good sense of what our initial conditions should really be for planet formation. So I agree entirely with what you're saying.
Because this molecular viscosity is so far off that anything else will overtake it. You have to find what is the other thing.
Yeah.
There's another question.
Oh, thank you. Yeah.
Do you have any good papers for reference for the number 2 solution?
Zhuining Bai has written a lot about this. There's also another group whose authors are escaping me at the moment. Does anyone know? I'm sure Zhuining cites them.
Ruth, you introduced Q, but didn't calculate it. Are you planning to do that?
So I said that Q for the minimum mass nebula was something like 30. Yeah, 30 to 100. It depends on what numbers exactly you put in. So there's a lot of room to make a more massive disk above the minimum mass nebula. But you're right, I didn't calculate it. I just said that. I didn't write it down. Okay. So how do you get the temperatures in these disks? And that's the last piece to understand not to understand what they're like, but to understand what you would need to understand to know what they're like. And I'm just going to just roughly sketch, how you do that calculation so that we can get to looking at observations. And okay, so temperature. So you could, if you're an actively accreting disk, then you can actually be heated by that accretion, right? Because as Scott showed yesterday, orbital energy E as equal to negative GM over 2A at A. If you go to half your distance, you're going to have negative GM over 2A over 2 is equal to negative GM over A. So your energy you have to dissipate to move to half separation is about equal to your starting energy. Well, it's equal to it. So what that means is that, as material is accreting, you have, you're dissipating an amount of energy per area that's about equal to the orbital energy of the material, or the gravitational potential energy of the material that's falling in. And that's going to be balanced by 2 times the Boltzmann constant times the surface temperature to the 4th power. And then there's a coefficient that comes from the fact that, that I left some coefficients off. Okay, so this will give you the temperature that's determined by accretion, that's generated by accretion, with one further caveat, which is that if you're optically thick, your surface temperature is equal to your midplane temperature divided by your optical depth And I can go back and do that calculation if people would like, but I do want to move on to looking at observations. So ask me if you'd like to see that later. So we have to multiply this thing on the right-hand side by either optical depth, if you're optically thin, or by 1 over the disk optical depth, if you're optically thick. Okay? So that's one place you can get temperature from. And the other one is you can get it from just being irradiated by your host star. And remember, if you're doing this calculation, you should go back and actually find some pre-main sequence tracks for the star that you care about, because its luminosity is probably different than old ones. And so you have a passive disk. They're flared. You have some surface area here that's being illuminated. So our luminosity of our star is distance r by 4 pi r squared times that surface area times a geometric factor that's essentially dh dr, which is like h over r. That's the amount that this patch is grabbing from the star, and that's like sigma t to the 4th times the area. So the areas cancel out. Remember that scale height is CS over omega, so it depends on temperature. And you'll get a temperature if you do this that's proportional to the r to the minus 3/7, which is not so different from r to the minus 1/2, which is what you would just get for a sphere that's being passively irradiated. Okay, so that's just a sketch of how you would get temperatures. In practice, what ends up happening is that for reasonable accretion rates, accretion matters a whole lot in the inner disk, all the way out to a few AU. It dominates the temperature. And in the outer disk, you're always passively irradiated. And then once accretion stops, passive irradiation gives you your temperature. All right. So, yeah. This is 3/7. Here, I could show you. H is CS over omega, so that's proportional to t to the 1/2 over r to the minus 3/2. So now we have t to the 1/2, r to the 3/2 over r squared, r cubed is proportional to t to the 4th, which is 8/2. So we have t to the 7/2 is proportional to r to the minus 3/2. So we have t proportional to r to the minus 3/7. Okay. Right. Yeah.
So the curved bracket and the second one was the actual optical.
Yeah. It's actually 1 over tau, and the reason is that if you have a disk that's optically thick, you have a temperature at the midplane, then your photons have to random walk to get out from the midplane.
Yeah, because the common coefficient, the
Oh.
amount of the curved bracket,
Oh.
each surface is
Thank you. Thank you for correcting me. Does that solve the problem? All right, good. Okay. So what can we actually observe about these things? And I guess I'm going to write one more thing on the board before I turn on my laptop, but it's a really quick thing. And that is just to remind you, right, that for a black body, H nu is like KT, right? A black body is all about thermalizing your photons. The photon energy is just KT. So HC over lambda is like KT. So lambda is like HC over, over HC over KT. And really, if you want to get the maximum, then you want to divide by 5 for your black body curve. But the point is that the peak, in terms of wavelength of your black body emission, goes as 1 over temperature. Okay, so I'm going to can I turn my computer back on? Yeah. So, just while it's happening, optical depth here is surface density times opacity. No, you can put it down. You can put it down. Where your opacity is in centimeters per gram. Okay, there you go. So your opacity is just your cross section for scattering photons, normalized to the total mass that you have. Actually, this is important for looking at these observations. Whenever you're working with optical depths and opacities, you have to remember what mass it's being normalized to, because usually it's normalized to the total gas mass. And the dust is what's actually doing generating the opacity. Let me try. I can. Okay, great. There it is. Okay, great. So that was the zodiacal light. Okay. All right, so someone asked earlier, what are the accretion rates? So let's go through some of these observations. So here are the observed accretion rates for protoplanetary disks. Remember, we're talking about unobscured disks. This is as a function of log stellar mass. So here where it says 0, that's for a solar mass. Right? Yep. And these are lower mass stars, higher mass stars. You can see that this is log accretion rate in solar masses per year. For a sun-like star, a typical number might be 10 to the minus 8 solar masses per year. There's a clear trend here, but at any given stellar mass, there are 2 orders of magnitude in dispersion. Yeah?
How are these inferred?
Good question. That's what I was about to say. So we're on the same wavelength. Okay, so how are these inferred? The most direct way to infer this is to look at accretion shocks on the surface of the star. So we just said that as you move from one distance to half your distance, you dissipate approximately your orbital energy. So if you do the exercise of saying you go from a couple of stellar radii to the surface of the star and ask how much energy you dissipate when you collide with the surface of your star, and actually it turns out over those distances, material generally flows along magnetic field lines, so it really just does smack into the surface of the star. You'll find that the temperature at the surface of the star, and it's just that same calculation, in the spots where accretion is happening, is something in excess of 10 to the 4 Kelvin. I say in excess because if you do the really quick calculation and just assume it's hitting the whole surface of the star, you'll get 10 to the 4 Kelvin. But really it's being funneled along magnetic field lines, and it'll be over a smaller area. Yeah?
I realize it's not your work. I wonder if it go down to 1 plus 3 or
I don't know the answer to your question.
I guess.
Yeah. I hear your question, though, as a relevant one. Yes. Okay. So anyway, the surface of the sun, right, is 6,000 Kelvin. So 10 to the 4 Kelvin or hotter is hotter than the surface of the sun. We know that the sun peaks in optical wavelengths. So if you go ahead and do that, peak wavelength calculation that we just did, goes as 1 over temperature. It'll be at shorter wavelengths. You'll find that it's in the UV. The UV is very hard to observe. You need to go to space because, thankfully for our health, the atmosphere absorbs in the UV. So the best measurements of this are from UV space telescope measurements that can do essentially that accretion shock calculation and measure the accretion rates based on how hot the accretion spots get due to accretion. However, because that's difficult, frequently what's done is to use H alpha as a proxy. And H alpha, the H alpha line turns out to be an okay, though not a fantastic, proxy for accretion rate. So I don't remember how many of these are from each of those methods, but those are the two ways it's done. So again, there's a trend, but a lot of scatter at a particular mass. 10 to the minus 8 solar masses per year is, a reasonable number that you could quote for a solar mass star. And I'll just comment about that if you take 10 to the minus 8 solar masses per year and multiply it by a few million years, which is the typical age of one of these disks, which I'll show you in a sec, you get something like 30 Jupiter masses of gas. And if you say 100th of that is in solids, then you get something like 100 Earth masses of solid material, which is actually not all that much more than the total inventory of solid material in solar system planets, which I think is interesting because what that says, to me at least, is that you cannot make a model where you're essentially accreting at these observed rates in steady state, and that's all the material that you have to work with. You either have to have laid down a more massive disk in a dead zone at early times that you have to work with, or you have to have solidified solids out of the early accreting material. Yeah?
Yeah, I think that's an interesting point. And also, but, that's also in favor with the, H and tau, you don't know what the wings are, but so we know that H and tau is a really young system, and you see some kind of wing structure. And in the early phase, you have much higher accretion rates. So altogether, if you integrate these accretion rates, then you have much higher mass than now, right?
Yeah, so you have a higher accretion rates at early times. So, right, so if you go to early times, you have more mass. If you go to early enough times, you have the whole mass of the star. Right, so this is exactly what I was saying. It depends on when you're talking about, and you have to think about that. Well, these are measured current accretion rates. Yeah. So I'm not familiar with the latest ALMA data on that, but we definitely know that accretion is bursty. We know that there's actually a very basic reason that we know that, and that is that if you go and look at the accretion rates onto protostars and then add up the statistics and try to make the stars out of that accretion, it doesn't work. You don't have enough accretion onto the star. And the way to get around that is to say they spend short periods of time accreting much more quickly and longer periods of time accreting slowly. And there are models for why that might happen, including just clumpy infall at early times, and thermal instabilities have been suggested that generate epiorionous outbursts at later times. But yes, regardless of what the answer to that is, accretion is clearly bursty, at least at early times. And I'll put up HL tau in a moment, so if you have more to say about that system when I do, let's come back to that. Okay, so these were the earliest types of observations of these disks. This is called a spectral energy distribution. This is wavelength. Here's wavelength times flux flux per wavelength. So this has scales as energy per time per area. And what you're looking at here is a black body curve from the star. And then as you go to longer and longer wavelengths, this is just a superposition of more black body curves from lower and lower temperature material. And this is coming and again, this is because the peak of your black body goes as 1 over temperature. So longer wavelength peaks are from lower temperature material, and this is the signature of a disk sitting around a star. Until there was imaging of disks, it wasn't possible from these curves to uniquely determine the sizes of disks, because there's a degeneracy in these plots between the grain's distance from a star and a grain's size. And that's because small grains don't efficiently emit at long wavelengths. So it turns out that the grain properties actually affect the details of what temperature you're going to get for an individual grain. And there's a degeneracy, again, unless you have imaging to see what distances these grains are at. This is the same sort of spectral energy distribution for what's known as a transition disk. Here, the hot part of the disk, the smaller wavelength part, is missing. And now that imaging has come in, it's been verified that these dips come from holes in the center of disks. So these are disks that have material at large distances and not at small distances. So these are called transition disks because the assumption was that this is a phase that most disks go through. It's the transition to being a non-disk. And the statistics, about 10% of disks are these transition disks. And so this was taken to be evidence that the clearing time scale for a disk, once it started the process, was something like 1/10 of the lifetime of a disk. The lifetime is a few million years, so this would be about 10 to the 5 years. However, more recently, or maybe then as well, but currently the most favored idea about these disks is that these holes are actually cleared by planets. If you like that idea, they have to be cleared by giant planets. And we heard earlier, or maybe I forget if you actually said this, but the giant planet fraction looks to be something like maybe only 10 or 20% of stars. So you could alternatively say that this has nothing at all to do with the timescale for disk clearing. It's just the fraction of stars that have giant planets. So I think that's a thought that needs to be further followed up as we start seeing, planets in these disks. I'll just quickly point out again that when you look at disks, the grain size determines the opacity of your disk. So this is opacity. So this is again cross section per mass for photons in a disk for different grain size distributions. And I'll just say a couple of things and point a few things out. So if you have a large grain, it's just like a big solid thing. Its opacity doesn't really depend on wavelength that much. If you have a little grain, Rayleigh scattering happens. Its opacity depends a lot on wavelength. It goes as wavelength to the -2 power. I started really late, so I'm going late. So if you look at this, if you have a grain size distribution that goes to much larger sizes, then you'll have an opacity that's flatter as a function of wavelength than if you only have really small grains, where it's steeper because more of your grains are in that Rayleigh scattering regime. And the other point I'd like to make with this is just to point out that the opacities are smaller at longer wavelengths. So at longer wavelengths, you can actually see through to the midplane of your disk more effectively. So longer wavelengths are where you can start measuring disk masses more easily, because you're not just looking at the surface of your disk, you're actually seeing through all the way to where it's optically thin. So disk masses, and I'll show you a plot in a second, have been measured in the outer regions of the disk at longer wavelengths. Yeah?
What's the origin of the bump in the
I think that these are silicon. So this is all grain. This is grain scattering properties, and I think that this is a silicon resonance feature. That's great. All right, cool.
What are those bump lines?
I don't remember. I didn't make this plot. This is from Andrew's 2015. This is a nice review. This is a review article on these sorts of measurements, so I recommend it. It's fairly pedagogical. I don't remember what the dotted lines were. Okay. All right. So here's some information about disk profiles. Again, from this is actually work mostly from Sean Andrews, but the plot is coming from his review article. And here are these gray curves are fit measurements to the surface density as a function of distance. Ooh, it got cut off. This is distance from the star in AU for a bunch of observed disks. And these observations were done I'll point out a few things. These observations were done in the millimeter at long wavelengths, again, because that's where the opacity and the optical depth of the disk is low enough to see to the midplane. They only are at large distances. That's not just resolution. It's partly resolution. It's also, again, because you need to have a low enough surface density, which you get at large distances, to go to the midplane. But it's actually mostly just resolution. They don't have resolution on the interior here. Here here are a bunch of these disks. The blue boxes here are the wide and chilling minimum mass solar nebula. The black dashed line is the Hayashi minimum mass solar nebula. So there are a couple of things. First, that's actually pretty good. You know, who would have thought? But remember, these are all old, unobscured disks that they're able to see. This is not at early times. These are very, late stage disks. Second, if you sort of do an aggregate of these profiles, it looks less like an r to the minus 3/2 power and more like an r to the minus 1 power. So you can see there's a range in here. Right. Yeah. That's correct. They need to know the temperature, and that's the last thing that I wanted to point out here that I forgot to say is that this depends a lot on what you assume about the grain properties in your disk. So that previous plot was showing the differences in opacities that you got if you chose different grain properties. You can actually, if you have an image of a disk and you have its SED, you can learn something about the grain properties by using the image to tell you the size of the disk, and then using the grain properties to fit the SED. And if you do that and take an aggregate measurement and do something reasonable, then that will tell you how do you use your grain properties as a function of temperature, and then allow you to infer your temperature. But it is there is uncertainty in this for sure, based on that. Yeah.
Yeah, I just want to comment that metallicity is also important here, and that should give another factor of something like 3 of uncertainty in sigma. Because here it's probably constant metallicity or stellar metallicity, but this will increase the spread.
That's an excellent point. All of these measurements are done just with the just with the dust, not with the gas. And so you can't see the gas directly. What we're trying to measure here is surface density of gas, but what we're actually measuring is surface density of dust, then there's a correction factor, and we don't know what it is, so that's an excellent point. I mean, sometimes you have some information, but not always. Any other questions before I move on? All right. Oops. Okay. So what can we say about the composition that is of material in these disks? So now I'm going to go through some highlights of things that are interesting. This is ALMA Cycle 1 data, 2015. So this is hot off the presses. This is a protoplanetary disk. And what this is an image. Here's the actual image of lines of this funky looking chemical. But the point of it is that it's a proxy for where CO solidifies into solid material. So you see this chemical where CO has turned into ice. And you see, here's the model. This particular ring is at 90 AU, which is at 25 Kelvin. So in this disk, this is the temperature at which CO solidifies. And here's the residual. So this is the kind of data that's starting to come out of ALMA, which is very exciting. So I'll just make a brief point here, which is that the chemical composition of these disks is coming largely from processes actually in the interstellar medium, except right near the star where it gets hot enough for chemical reactions to substantially change the mix of molecules. When you're looking at these disks, you're mostly starting with an inventory from the ISM, and then what you want to know is whether you should apportion the inventory of each of your molecules into ice or into gas. So on the one hand, that makes your calculation of what's around a little bit easier, but on the other hand, it makes it dependent on what you got from the ISM. So it's harder. Okay. So, but I'm excited about this, actually getting some measurements of snow lines, these disks. Here's another image of a protoplanetary disk. This is not in long wavelength light. This is from SEEDS, from Subaru. This is an optical image of polarized scattered light, but of a gas-rich young disk. And look, here you can see these beautiful spiral arms. So a few of these disks have now been observed with spiral arms. When I mentioned spiral arms before, it was in the context of an infalling cloud driving self-gravity in the disk. And I suppose that's possible in this case, but this isn't heavily obscured, and there have been some really interesting there's been some really interesting work lately suggesting that a very massive planet, actually sort of bizarrely sitting at the ends of one of these arms, can produce this sort of arm structure. So this may be an indication of planet interaction, and I think we'll have a planet-disk interaction talk later in the school. Here's HL Tau. This is what came up before. This is a very young star. It's thought to be only about 10 to the 5 years old. This is, again, at long wavelengths. This is with ALMA. It's finally been published. It's about at millimeter wavelengths. Here's the scale. And this is just really unexpected. You know, if you were asking me about a young disk, I would have expected maybe to see some arms, maybe to see some gaps with some, you know, tidal streams from planet interactions. Well, you know, I'm sure we'll have a much longer discussion about this, you know, later in the school. But these rings look sort of bizarrely clean and circular and yet large and deep. It's really sort of weird. I'll just make one comment now about this, which is that you know, there are other ways that you could imagine getting this sort of structure other than planet interactions. People have talked about generating overdensities in the disk that attract small material into rings. And one way that I think is sort of interesting that could happen is actually related to those non-ideal MHD models of accretion that we mentioned earlier. Simulations that both Schwenning and the other group, whose name is slipping my mind, are doing in boxes actually show zonal flows resulting in the outer parts of disks from, you know, from accretion when you include non-ideal, you know, partially ionized disks. They haven't been able to do global simulations yet, so it's still not clear whether you could get something like this, but it actually is a possibility. So it's worth thinking about alternatives to planets in this case. All right, so I said we've mentioned several times that the disk time scale for depletion is something like a few million years. Here's the data that says that is so. Here's disk age. This is a review article from previous work. Here's disk fraction. This is, again, those infrared excesses that we saw in the SEDs. Yeah?
Another paper by Falsman, where they suggest, or they argue that there's a strong observational bias for the disk ages, because you're biased to, I don't know if you can call it. So I think because like most of the disks you observe are like clusters and more like in the denser population of the clusters.
Mm-hmm.
And but most of the stars actually are explode outward, and you might actually you might expect to get longer longer disk ages. That's just sort of, I mean, I'm not an expert on that, but I'm curious if you are familiar with that.
I'm not, and that's an interesting idea. I understand what you're saying.
It could actually, I mean, that would be really interesting also for planet formation.
Yeah. Yeah, it's quite interesting. Yeah, be nice to have the reference. So here's disk. So with that caveat in mind, right? Here's the disk fraction. If you go out to a couple million years, you still have most of your stars having disks. Go out to 10 million years, they're basically all gone. So that's the basis for saying that disk lifetimes are a few million years. Now I'll show, just to end, I'm going to show some images of debris disks. So all of the ones we've seen so far are protoplanetary disks. You still have gas around. That's where planets are forming. And just before I show the images of debris disks, I'll just point out that though grain's thermal emission, that long wavelength emission, is isotropic, scattering of optical light from the star is not. So when you're looking at debris disks, you're mostly looking at scattered optical light. And one side of your disk is often much brighter than the other because depending on your grain properties, either forward scattering from this part of the disk or back scattering from this part of the disk will be much more efficient. Usually it's forward scattering, but in principle it could be either. So here are some debris disks. This is the moth. Looks like a moth. This is thought to be a disk that's actually moving this way, interacting with the interstellar medium, being blown backward. Here's Beta Pictoris. This is actually a really old image of Beta Pictoris, and the reason I put it up here instead of one of the newer ones is here's the disk. Here's this warp in the disk. This is one of the, relatively rare triumphs of predictive theory. Anne-Marie Lagrange and her collaborators predicted that there would be a planet in here generating this disk warp. And indeed, she has since found it. Here is a very up-to-date image. This is the AU Microscopiae debris disk. This is from SPHERE. Oh, I didn't write SPHERE. Oh, no, I did. There it is. SPHERE, which is a new imager in Europe. You see these beautiful, bizarre little bumps on one side of this disk and not on the other. This is a very edge-on disk. That's interaction of some sort, and the fact that it's over here and not over here is really weird. So this is a really exciting observation. They've also shown, by going back to archival HST data, that those bumps existed in the HST data at early times. They were just less believable because the data wasn't as good as the SPHERE image. And they actually appear to be moving over time. Really odd. Yep.
Aren't those bumps moving faster than the escape velocity of the system too?
That is correct. They look like they're moving slower than the escape velocity, then faster, which could be to say that they're being blown out by radiation pressure, for example, at faster than the escape velocity, and you have a projection effect over time. But yeah, it's I'm really excited about this image, and this one, which is coming from the other new imager, the Gemini Planet imager, GPI, of another debris disk. And this one, you see a disk in the interior. It looks like a ring. There's a hole in the middle. You go again to HST data, and at larger scales, this big flare, and yet a flat part on the other side. And that also is pretty difficult to achieve, getting interesting structure on one side, but a nice calm, flat other side. So these sorts of images are just starting to come out of these scattered light imagers, and I think they're going to give some really interesting dynamical results. This actually is a companion to the system. This is the scale bar got cut off. This is something like 500 AU here. So this is a factor of 10 larger than this. This is sitting in the middle here. And this is a 10 Jupiter mass class object. But it's really difficult to make this with this. So this is a dynamically disturbed system. And I think my time is up. I'll just end here with Fomalhaut, which is one of those 4A stars, I think.
It is?
Yes, right?
What are the other three? No,
Sirius. Vega. Anyway, I'll leave us with Fomalhaut, which is this beautiful debris ring. As you know, a point was found in here, which may or may not be a planet on a really bizarre orbit. And but it's whatever it is, it's a beautiful debris ring. So I'll leave that for Planet Disk Interaction Day or not, depending on what happens then. Okay, thanks.
Thank you for this excellent talk. Maybe one or two questions, if you still have, because you asked so many, which is good. Is that a question?
No,
Comment,
You
yes.
say about the magnetic effect that, if I understand, the plasma beta, the pressure over the magnetic pressure is huge, but the magnetic field is still important.
Well, it depends on what you assume the plasma beta is, and we don't actually know. You can't directly measure it. So the wind effect that I talked about definitely depends on assuming a strong vertical magnetic field. And the idea is that it got pulled in from the protostellar cloud.
Regarding the heliosphere, there's an envelope information about the cascade of the you say that there's a turbulence and there's magnetic field. There's two different solutions to this problem. If I understand correctly.
Well, there are magnetic fields in both cases, but you could have turbulence that could, or you could have a wind. Yeah.
And I'm talking now about magnetic turbulence.
Yeah.
The non-Colgomoro, which we received in today's precision 2 years much better when you send the satellite to the corona. And as a result, you can assume that the cascading to the smaller structure, eventually it interacts much better with the, I believe, with the dust and the gas, maybe. And all the assumptions which are given to maybe modified in the magnetic turbulence.
Yes, I think you can generally say that we don't understand how the magnetic fields are operating in these disks, and that uncertainty comes into both of these types of models. And I didn't talk about what you're saying, so you've added an additional way that that's uncertain. So thank you. Yeah.
Okay, let's thank Ruth again. Thank you very much. We're going now for lunch at the Belgian house, not the same place